So perhaps to set the stage of my life's work on the autonomic nervous system mostly. The autonomic nervous system, of course, is that part of the nervous system which controls all the visceral organs, the gut, the blood vessels, the heart, and so on, the uterus, automatically. And the autonomic nervous system has three components to it. It has sympathetic nervous system, it has parasympathetic nerves, and it has enteric nerves, the nerves in the gut. And most people are surprised to hear that there are hundreds of millions of neurons in the gut, more in fact than are found in the spinal cord, as well as glial cells, enteric glial cells, which are very similar to the astrocytes found in the brain. So when I was in Oxford, the preparation that was developed by Edith Bulbring, the Taenia coli, is a strip of smooth muscle on the cecum, actually, but it's innervated, has nerves supplying it. And these are nerves which are a mixture of sympathetic nerves, probably some parasympathetic, and certainly enteric neurons, extensions of those neurons. That's developed from different neural crest tissue from sympathetic and parasympathetic nerves, completely separate system. So all these nerves are in the preparation. So when you stimulate it transmurally or electrically, you're stimulating all the nerves. And the sucrose gap worked very well for the Taenia coli, the one I developed. And so when I got to Australia and got grants and the sucrose gap set up, I had two young men working with me, Max Bennett, who was a part-time technician finishing an engineering degree, and Graham Campbell, who was doing a master's degree with me. Then, I think it was just before Christmas in 1962, my young colleagues and I decided, well, we'd knock out the classical transmitters, acetylcholine and noradrenaline with drugs, atropine and guanethidine, and probably stimulate the muscle directly. And we expected the preparation to depolarize the smooth muscle and to be followed by contraction. What we saw, to our amazement, and we all knew that something important had happened, but to our astonishment, what we saw in response to single stimuli were hyperpolarizing responses. And when you stop stimulating, this is at 1 hertz, then you get a contraction, a spike followed by a contraction. This was very puzzling. What on earth could this mean? How could this be due to direct stimulation of the muscle? This was debated in Oxford and other places. Nobody quite understood it, but I was lucky that I had a postdoc from Japan who had a friend in Japan who just published a paper on the discovery of tetrodotoxin from the pufferfish. And the tetrodotoxin is a marvelous drug because it blocks nerve conduction but doesn't affect smooth muscle activity. And tetrodotoxin completely blocks these hyperpolarizations, so we knew they were inhibitory junction potentials in response to a non-adrenergic, non-cholinergic, later called NANC, transmitter. But it was serendipity in a way. I mean, it wasn't a hypothesis at the time at all, but we were quick to know that there was something important there. I think that's a key. It's the anomalies in science which are the exciting things. It's not the what you predict.